Hello everyone, this is Ghorbani. I'm a PhD student at the Department of Structural Engineering and Building Materials at Ghent University. Today, I'm going to share with you some of our new findings about the influence of water to binder ratio on workability and strengths of ternary slag-based alkali activated materials. As an overview about the contents that's going to be presented during this presentation, I have divided my presentation into 6 different parts. The first part is the introduction part, which covers the importance of sustainability and alkali activated materials, which will be followed by the test matrix, the materials used in the study, the testing program, the result of fresh and hardened properties of the concrete mixtures, and in the end, the conclusions. As we all know, one of the main causes of air pollution in the past decades is the production of cement, which is reported to account for 7 to 8% of the CO2 emissions resulted from human activities. Therefore, the use of cement needs to be reduced to achieve the goals of sustainable development. In recent years, the growth of industrial activities around the world has led to a large production of waste materials which have a negative impact on the environment. Using these waste materials in the construction industry can provide a significant contribution in terms of environmental and economical aspects. Alkali activated materials, which are known as clinker-free cement, has been of a great attention through these years due to their lower CO2 emissions, lower energy consumption, equivalent harden and durability properties compared to ordinary Portland cement. Alkali activated materials are produced by activating an aluminum silicate precursor, which can be ground granulated blast furnace slag, which is abbreviated as GGBFS in this study, fly ash, stainless steel, copper slag, and etc., which is activated by an alkali activator. Through these years, GGBFS and fly ash have been the most aluminum silicate industrial byproducts used for the production of alkali activated materials. However, there is a big challenge nowadays of these waste industrial byproducts, which have made them less available compared to the past. Therefore, the use of new sources of solid precursors needs to be developed for the production of alkali activated materials. Based on this introduction, and since stainless steel and copper slag can be found in the huge amounts in Belgium, in this study, we have come up with the idea to use these two less frequently aluminum silicate sources as solid precursors together with GGBFS for producing a ternary alkali activated concrete mixture. To this end, based on the achieved results on mortar level, the most promising ternary mixture, which consists of 50% copper slag produced by a local company called Metallo in Belgium, 35% GGBFS produced by the company of Ecosam, and 15% stainless steel slag produced by the local company of Orbix was taken to the concrete level. In total, 3 concrete mixtures were prepared using 3 different water to binder ratios to study the influence of different water binder ratios on the fresh and hardened properties of the ternary alkali activated concrete mixture. The molar ratio of all the ternary concrete mixtures was kept constant as 1.3. In this slide, we can see the mixed proportions of the ternary concrete mixtures. What we can say about this table is that the total amount of solid precursors was kept constant as 400 kilogram per cubic meter. The ratio between fine and coarse aggregates was considered in a way to approach the ideal grading curve as defined by DIN 1045-2. In this slide, we can see the chemical composition, the physical properties, and the particle size distribution of the solid precursors. As can be seen in the chemical composition table in the right side of the slide, the copper and stainless steel slags showed lower contents of alumina and silicate compared to GGBFS, indicating that they are less reactive. It can also be seen in the physical properties table that the copper slag displayed the highest specific gravity, which is 3.45 compared to steel slag and GGBFS. As can be seen in the right side of the slide, the particle size distribution shows that the copper slag consists of a broader range of particle size compared to GGBFS and stainless steel slag. In order to activate the solid precursors, two different activators were used and mixed with each other to come up with the alkali solution. For this sodium hydroxide pelts with a purity of 98%, sodium silicate with actual mole ratio of 2 and density of 1.53 produced by PQ Corporation were used. Next to the precursors, an alkali activator, fine aggregate with the range size of 0 to 4 mm and coarse aggregate with the range size of 2 to 16 mm were used to make the concrete mixtures. In order to evaluate the effect of water to binder ratio on the fresh and hardened properties of the ternary alkali activated concrete mixtures, a set of tests were performed, such as slump bursting time, fresh density, isothermal calorimeter, and compressive strength. The slump bursting time, fresh density, and compressive strength of the alkali activated ternary mixtures were done based on the Eurocodes. In this slide, we can see the slump as a function of time of the alkali activated ternary mixtures together with their fresh density. As can be seen in the right figure, which represents the slump over time of the alkali activated mixtures, using lower water to binder ratios lead to lower slump values of the concrete mixture, which can be related to the acceleration of condensation process as a result of using less content of water, which results in shorter setting times and rapid hydration reaction. It can also be seen that all the AAM mixtures displayed a slump class of S3, S4 for at least 30 minutes. The slump of the concrete mixture with the water to binder ratio of 0.32 begins to drop down significantly after 30 minutes, while this is the case after 60 to 75 minutes for the concrete mixtures with higher water to binder ratios. The mixture with water to binder ratio of 0.32 displayed a lower slump value of 13% and half and 18% after 30 minutes compared to the mixtures with water to binder ratios of 0.34 and 0.36 respectively. As can be seen in the right table, the AAM mixtures displayed the same fresh density, indicating that the water to binder ratio did not affect the fresh density of the alkali activated ternary concrete mixtures. In this slide, we can see the isothermal calorimeter result of the paste samples. In the left figure, we can see the rate of hydration hit, and then in the right figure, we can see the cumulative hit result. What we can see in the left figure is that the alkali activated paste samples displayed two main peaks. In the first peak, which occurs a few minutes after the contact between the water and the solid precursors, there is not that much difference in the intensity of the peaks and also the occurrence of the peaks. However, with the use of water to binder ratios however, a difference appears visible in slightly earlier second peak for lower water to binder ratio, which the intensity of the second exothermic peak gets diminished using higher water to binder ratio. So what we can say in overall is that the use of water to binder ratios did not significantly affect the dormant period and the general trend of the heat evolution. In this slide, the compressive strength of the alkali activated ternary mixtures after 1 day, 2 days, 7 days, and 28 days of sealed curing in the curing chamber is shown. We can see that all the AA mixtures displayed a compressive strain values of more than 20 megapascal after 1 day of curing, regardless of their water to binder ratio, indicating a high strain concrete for precast applications. The concrete mixture with lowest water to binder ratio displayed the highest compressive strength in the all testing days compared to other mixtures. The concrete mixture with water to binder ratio of 0.32 displayed a higher compressive strength of 17.5 and 8% and 35% and 11.5% after 1 day and 28 days of curing compared to the mixtures with the water to binder ratios of 0.32 and 0.36 respectively. On overall, this is a limited impact on strength, making the longer workable time of water to binder ratio of 0.34 versus 0.32 an interesting option for the mix design in this study. In this slide, which is the conclusion and it's the representative of the most important findings of this research study, the most important finding can be listed as below. Using lower water to binder ratios lead to lower slump values due to the acceleration of the condenser process, resulting in a shorter setting time and rapid hydration reaction. The use of higher water to binder ratios did not significantly affect the dormant period and the general trend of the heat evolution. However, a difference appears visible in a slightly earlier second peak for lower water to binder ratio, which the intensity of the second peak gets diminished as using higher water to binder ratio. The compressive strain values between 71 to 79 megapascal are obtained after 28 days, and 1 day strain of already more than 20 megapascal, indicating a high strength concrete for precast applications. The concrete with water to binder ratio of 0.32 displayed higher compressive strain of 8% and 11.5% after 28 days compared to the mixture with water to binder ratio of 0.32 and 0.36 respectively. By considering this small effect of an impact of strength, we can say that the mixture with water to binder ratio of 0.32 is an interesting option for the mix design in this study. Thank you very much for your attention. Wish you all the best. Bye.